Hi, welcome all to the first lecture of Principles of Statistics. First, I'm going to start with an introduction, a very high-level introduction to the course, and then I will go into the first block or main block of the course, which is the likelihood principle. And on the way, I shall be explaining essentially the structure of the course, but I won't do that at the very beginning. It will just come naturally at every during the lecture. So you should now be seeing my tablet, or the screen of my tablet, and me on one side of the camera, and this in theory should be the format that we'll take for the whole course. So let's get started with the introduction. So I shall sometimes shorten a lot of words, as you can see here, and but that should be okay because you've got the recordings. So the first thing I want to say in the introduction is I want to make a very sort of generalized, careless, near careless, I guess, distinction in statistics between subfields, so that you understand where this course sort of fits in. So we have, first of all, probably the dominant community in statistics is what is called applied statistics. And then there is a smaller community that is basically theoretical statistics or mathematical statistics, which is, by the way, so it is, if you think of DPOMS, the department, and the last two letters are MS, and that is precisely standing for mathematical statistics, which is the main focus of the Stats Lab, although there are people, of course, doing more applied things. And let me also mention that, so in this distinction, what I, very, very vaguely define them to be, or the difference to be between them, is that an applied statistician will get a question that is very qualitative, right? So it's really, a real life question, and the job, the first part of the job is to translate this into some quantitative question. And then once you have this quantitative question, you can, you've really formalized things, and you can use existing methodologies if they make sense, or create your own methodologies. So that would be, very vaguely, the job of an applied statistician. And the job of a theoretical statistician is a bit different, because we will start with a quantitative question directly, and what we want to do is, because we have this formalized very well already, then is to study the methodology. So to try to put some theoretical guarantees on it, right? To understand its behavior, in many ways or many senses, each, appropriate for the application at hand. But the focus is really proving that the methodology will work under this or that condition, so just a theorem, yeah, or a proposition. Okay, so given this distinction, which is very vague, as I said, we're going to focus on the second. This course has the flavor of mathematical statistics, and so it combines maths, stats, analysis, and I think it's a really fun course for literally, it doesn't matter what your profile is. If you have a focus on pure mathematics, then you will enjoy this, because it has a lot of proofs, and you will see an application of some of the more theoretical, concepts that you've been learning so far. If you want to do more statistics, then that's actually, this course, you should definitely know it, even if you want to do applied statistics, because an applied statistician should always have seen some of these mathematical statistics results, so that they have a good foundation of what is true and under what conditions. And then if you are thinking, in a few years' time to do more like data science or machine learning, I mean, these are not, I wouldn't classify them as being part of stats, and you will really stand out in these fields if you, get a good grip of theoretical statistics, because, and again, this is a generalization, there is hardly papers and results in these fields that really would classify as mathematical stats, and there is a lot of there is a lot of need and interest at the moment, precisely. So it's a very hot topic, is to try to have theoretical guarantees for more machine learning or data science methodologies. Okay, so let's start with a recap of some probabilistic concepts that we're going to need, and also so that we can fix notation. So let's start with the probability space. So I will introduce a probability space first of all. So let me just make this a bit bigger, not too much. Yeah, should be fine. So let then this triplet be a probability space. So I remind you that probability space has the events space, the sigma algebra, and the probability measure. So this probability measure, by the way, I'm going to call it BBP, just because in LaTeX it is written as math BBP, so that's blackboard bold, and there will be a capital P. So I want to distinguish the two, basically, as I'm talking. Okay, so given this probability space, and that I want to embed the real line, or I want to, well, I guess I want to just consider the real line together with the Borel sigma algebra, the usual one. Then we have that we can consider real valued random variable. So by the way, we could consider more general random variables, but in this course, the focus is real valued, and so random variable I will shorten as RV, and this is given simply, I remind you, by a mapping that goes from the space of events to, in this case, the real line. And for it to be a random variable, it has to be measurable, right? Now, its distribution, we can define it. So its distribution is simply given by the following function. So this is distribution function. I'm going to call this capital F at t. T is a real number. And so this is going to be the probability that we assign under the BBP probability measure to the set of events such that the image or their image is less or equal than t. And again, this is for any t in the real line. Okay, so what can we, can we just refresh, again, our concepts from previous courses? Yes, we can. So let's talk about PDF, PMF. So the usual quantities. By the way, I'm using this bar here just to denote capital X. So let's assume that we have X discrete. So if we have X discrete, then remember we have we can have F. We can call, or maybe let's say let F of X, and X is going to be a real number. So this guy is going to be given by the probability of the capital X being X, and this is so we want this to be the probability mass function. Okay, usual concept. And so in this case, can we write the capital F in terms of the lowercase f? Yes, we can. So this is going to be the sum of all of the x's less or equal than t, and then we sum up the corresponding f's, right? Okay, or fx. Okay, great. Can we say more? Well, yes. I mean, the next thing that we have is a continuous, so we can consider a continuous random variable. And so let now, with the same notation, let f be the PMF, sorry, PDF. So this is the probability density function. And so then we can write ft. So now, we don't have discrete values, we have continuous values, so we need to integrate. So we take the integral from -infinity to t of the fx dx. Okay, good. So let's introduce one more piece of notation. So let's note, first of all, that in the definition of the capital F, so in the definition of the distribution function, we can write the right-hand side as follows. So note, ft can be written as the probability of the counter image of this set through x. Okay. So given this, we realize, of course, that this is just the composition of the two, well, of the measure and the inverse mapping, and this actually defines a probability distribution rather than on the space of events. It defines it on the real line, yeah, with the Borel sigma algebra. So let's define capital P to be the composition of the double BP and the x minus 1. And this is, by the way, this is called the image, or maybe let me carry on with capitals. So image measure, or also push forward measure, or perhaps more generally, this is called the law of x. Okay, and so once we have this, we can write then ft very simply as just p, or the probability that p will assign to the set minus infinity t. Okay, and again, this is all throughout, we're talking about the whole of R. Now, why is this important in any way? The law, well, the law will determine, okay, so if we fix the probability space first, then the law will determine the random variable, and the other way around, the random variable will determine the law. And the same happens with the distribution function, at least in one dimension, the way we wrote it, and also with the PMF and with the PDF. Okay, so just keep that in mind, that they are just equivalent ways of describing the randomness of a random variable. Okay, so good, we have now a probabilistic setting and notation. So now let's do some stats. So we're going to introduce observations, right? So that's what we need. We need to have some random observations. So let's consider then x1, and these are capital again, xn, and these are going to be independent and identically distributed copies of our friend capital X that has the law capital P. We call this a sample of X, or just simply a sample, and we say that this has size small n. So small n, I remind you, is the number of observations that we've got. Yeah? So that's the sample size. Good. So now we're ready to give the first definition that we need. So a statistical model for some capital X is, and I will pause here because it would be very good if you pause the video and try to get your own answer to whatever comes. And that is because I think it's really, really important to think about what a model is and what a statistical model is. So maybe pause for half a minute, 1 minute, whatever you want, and think about it a bit. And now let me give you the answer. So a statistical model for X is any family, basically. So it's any family that we denote by f theta. So this f now is a PMF or a PDF. And we can also, so remember this is a function on the real line, and we can, so we can, I may use also this notation, which is that you have two arguments. One is the sort of x, and then the other is the theta. And what is important is that this theta is indexed by what is called a parameter space. So that's one way of doing it, through DMF or PDF. And the other way of doing it is just simply through the laws directly, okay, or the distribution functions. And so again, we can write this here. There's any family, this or this, of PMFs, PDFs, or distributions for the law of x. And as I was saying, we call this capital theta the parameter space. Okay, good. Okay, so I mean, I hope it makes sense, the definition, that you somehow were thinking of things along the line of this, because what we really want, I mean, statistical model for a random quantity, I mean, we have a random quantity, and then we think, you know, think of, for instance, physics, where things, you know, where I guess we have very good equations to describe some things. Some of them are deterministic, but we also have, for instance, statistical physics. And there we have good sort of natural and physical reasons to believe that the equations that we construct make sense, right? So once we do that, we have a distribution. And so, of course, we assume that the randomness comes from that distribution, but it may be that we don't know exactly with what parameters or hyperparameters. And so then this becomes a family, and that becomes a model, a probabilistic or a statistical model, or it depends on what you're talking about, whether you're talking about the probabilistic mechanism that is underlying you know, the randomness, or whether you're talking about something you're observing, and then you would say you have a statistical model. Okay, so given this, let me give you an example, well, a few examples, very basic ones. So let's start with, maybe, so let's imagine that we have observations that are non-negative or strictly positive, actually, and you know, if these are continuous, you know, the observations come from continuous random variables, then we could think, well, why not to propose an exponential family of distributions as the statistical model? So we can do that. We have an exponential distribution with some parameter theta, and this theta naturally in an exponential distribution is always strictly positive, right? So here the parameter space is just 0 to infinity. Okay. So a second example could be, for instance, given by you know, a normal or Gaussian family of distributions with, so let's say that we fix the variance and then we let the mean vary in some capital theta. And so for capital theta, a natural choice would be the whole real line, and a different choice would be, I guess, you know, if you have whatever constraints in nature or whatever it is that you are observing, maybe you have to restrict it to some set, like -1 and 1. Okay, so far we've had one-dimensional parameters, but actually this capital theta can be as complex as we like. So we will see at the end of the course, basically the you know, the case in which the capital theta is infinite dimensional even, but let's not jump too fast into that. So what we are now going to consider, for instance, is a two-dimensional family of distributions or a statistical model. And so here the very natural choice is to take mu to be in the real line and sigma squared to be strictly positive, of course. And so what we have really is that the parameter is this vector, and the parameter space is just simply the product of these two sets, right? Okay, good. Right, so now we're ready to have a second definition, because I've already been sort of talking about these models, statistical models. And actually, let me just very, very briefly say something about the complexity of the samples of the parameter space. And this is that, I've talked about physics, but if you think of modern applications, so say like image recognition or image classification, in these, the space of all of the possible images is very, very complex, right? So that's probably an infinite dimensional space. And, in many occasions in practice, we don't need to give the exact, we don't actually have any idea of what the correct statistical model is. And we just have something that we consider to be sufficiently approximate, okay? And that's fine. That's fine, generally speaking, in practice. Theoretically, we're not going to be caring about that so much. Rather, what we want is that we have correctly specified the model, and ideally also to do maths. That would mean that there is some sort of existence that we'll see now, and then we also want some sort of uniqueness, and that is that the data comes from exactly just one distribution in the family. Okay, so let's put this in words. So definition 2, a statistical model. And so we can write this as just simply through the P's. So P theta for some capital theta, and this is for X, this is correctly or well specified specified if for all theta there exists a theta, this parameter space, such that the P, which is the law of this capital X, equals P of theta, okay? For, for that P. Okay, so that's correctly specified. Let me now say what identifiable means. So maybe let's do semicolon. So, and it is identifiable if having two distributions in the family with different parameters necessarily implies that theta 1 equals theta 2. Okay, so this is the existence and uniqueness that we sort of wish to have. Just simply, in many occasions, it's simply just not to complicate things, but it is certainly necessary. It is certainly the assumption we will be, the two assumptions we will be considering in this course. Okay, so a remark about this. So the remark is the following. In a okay, so I will first of all write it and then comment on it. So in a correctly specified and identifiable model for X, we will often write, remember we have a unique theta, so we will often write theta naught for that unique value, okay? This is for, so to say, the true parameter. For two parameter for P, say, okay? It will not always be the case. In fact, in this lecture, we will not necessarily always use this, but I will be careful to mention when we are using it and when we're not, okay? So it should be okay, I think. Okay, and let me also say that still, even though we have this convention, we'll still say that if that I guess that x1 to xn as a sample, and these are capital letters, of course, are ID. So once we have proposed a model, So these are IID from the model, yeah, from this. Even though, of course, with at least what I was given, there should be just a unique value that corresponds to the distribution, that defines the distribution. Okay, good. Just to emphasize this, what we assume is that there is a unique theta naught that then gives us, or that indexes the distribution that the data is arising from. And this is, by the way, what is called frequentist. So frequentist approach or philosophy. So maybe let's say philosophy, or yeah, I guess school of thought, as opposed to, I mean, there are two main philosophies of thought in terms of how you understand randomness. And here what we're saying is that it comes from a fixed distribution. Now you could have also a Bayesian philosophy that sort of starts with the same idea. You have a model, a statistical model, but then rather than the data arising from a fixed value of theta, what the Bayesian philosophy says is that actually you have a random distribution also on top of this parameter. Okay, so you not only have the statistical model, but also a distribution on the parameter. And so the parameter is random, essentially. And so traditionally there's been, there's a long-standing sort of argument or discussion, or however you want to call it, between the two sort of philosophies, but we'll see in this course that actually we can analyze Bayesian procedures, and the Bayesian procedures, which is not the same as the Bayesian philosophy, so it's just simply the Bayesian method, that can be understood from a frequentist point of view as well. Okay, and that would be I think it would be an interesting piece of information for you. But we will always focus on frequentist philosophy in this course. Okay, so let me now go into, so we've spoken about probabilistic concepts, then statistical concepts. So let me now talk about the main goals of statistical inference, which is what concerns us here, of statistical inference. So the very first goal, and this shouldn't be a surprise, is estimation. So, under this frequentist point of view, there is a true value that is theta naught that we want to understand in some way. So maybe what we want to do first is to construct an estimator, theta n hat. And this, to be an estimator, has to be a mapping, a measurable mapping of the data. Okay, that is, for it to be a good estimator, or ideally, what we want this guy is to be close to theta naught. Okay, in this case, but actually, more importantly, let me remove the naught there to theta, just simply theta, when P equals P theta, and we want this for all theta in the parameter space. So as I said, even though here maybe it makes more sense to have a theta naught, I will just write theta, because the important bit is that it's got to be for every theta in the parameter space. Why is that? Well, if you're trying to estimate a parameter with your data, then of course you have no clue what the parameter can be within the space. Maybe you do have some sort of understanding, and therefore you can restrict your parameter space, but in general you will not know it, because otherwise what's the point of making estimation, right? So we really want this type of uniformity, and this is very important in mathematical statistics, to have this, and also in practical procedures, any guarantees should be holding across the whole parameter space. Okay, so second goal is hypothesis testing. So hypothesis testing. Okay, so in any hypothesis test, you should remember always that you're going to be testing two hypotheses. So this is the null hypothesis. For instance, let me give you an example. We have that this theta, which is now like this theta. So it's really just, the theta of the distribution generating data. We want it to be equal to some theta naught that is not necessarily the true one, but it's just a fixed value. So that's generally called the theta naught. So this is the null hypothesis. And then we have an alternative hypothesis, which in this case is just the complement. So let's say this is not that theta naught that we have in mind. Okay, so then what we want to do here is to build a test that generally we will denote by this psi n, and this psi n is again a measurable mapping or measurable function of the data. And you would say, well, then that's an estimator. Indeed, it is, under the definition of estimator, but it's a very, very special estimator, because what we want to have is that, well, first of all, it will only take two values, 0 and 1, and we want this phi n to be 0 when the null hypothesis is true, and we wish this guy to be 1 when h1 is true, okay? Now then you'll be thinking, well, isn't that a bit too ambitious? Because I mean, after all, you're saying that for a finite amount of data, you want it to be exactly know this when it is h naught, and when the null is true and when the alternative is. Yes, that is too ambitious indeed. Now, a different, a weaker way of portraying this is saying, well, actually, what I want is this to be true as I get more and more data. And so I want this to be true with high probability. So I guess approaching 1 as n goes to infinity. Okay, so this will be the type of, this is the type of asymptotics that we will be considering in this course. So as you get more and more data, this is what is called asymptotic statistics. As you get more and more data, then what happens to your statistical procedures? And now let me introduce the third main goal of statistical inference is confidence sets, confidence regions. So what we wish to have here is just to find an interval or a region. So it could be more general than just an interval. And what we wish for this, well, first of all, let's call it Cn. So C, again, this depends on the data, and what we'll have in the case of an interval is that the endpoints are now the measurable mappings of the data. If it is a more general region, then of course pretty much every point that features in this region is the mapping that has to be measurable with, well, they all have to be measurable with respect to data. And so we say that, we want to find this interval for a given significance level. So for a significance level alpha, this alpha belongs to 0, 1, such that we have the following. So we have that the probability of this theta being in the Cn is larger or equals, or is at least 1 minus alpha. Okay, and this is for all theta in your parameters. Okay, so let's recap a bit. So what we're saying here, so we start with this, that's the double BP measure. And the theta, so what we're saying here is that the data is being generated by the capital P theta for this given theta. So under that measure, so under the measure of the BBP for that theta, what we wish is that the probability of the theta being in this confidence interval or region that we've created to be at least 1 minus alpha. Okay, so this 1 minus alpha is what we refer to as the confidence level. Okay, And so of course it has to be this double BP theta, because this really is a set of events, right? So what you have here is that, yes, you want theta to be in this region, Cn, but actually this region is determined by these x's, which are mappings from the event space to the real line. And so really what you're looking for is for the events such that give rise to numerical values or real values of the x's that eventually give you a confidence, they give you an interval so that theta is contained. Okay, so let me make two remarks here. I mean, first of all is that we've introduced the term of significance level, and some of you will be thinking, well, actually that should have appeared in the hypothesis testing. And indeed it should have, and we could have included here some alpha value, and we should have actually done it, because for the tests, this sort of high probability comes sort of encoded through this confidence level as well. Okay, but I just wanted to introduce concepts little by little. And the second remark is that these confidence sets are very related to a very I guess a buzzword at the moment. So just so that you know that this is exactly the same thing, it's just being now named differently, especially in the sort of machine learning community. In stats, it's just confidence regions, but otherwise it's called uncertainty quantification. So what is this about? I mean, what we're doing, right, so if we think of the very first objective, that was to construct an estimator. So that is in a way to understand the parameter. But remember, the data is random, at least before you observe it. The data you observe, but the observations, when we start from this sort of mathematical formulation, then they are random variables. And then, of course, this estimator is going to be random through the randomness. And so if it is random, then what does close mean? So you want to quantify the uncertainty in your estimation, okay? And so a very, very common way of constructing a confidence interval or to quantify uncertainty is to look for the distribution, or to try to work out the distribution of this theta n hat. And then you know that if this is getting close to a parameter, to the parameter of interest, then all you have to do is to rule out the tails, in some sense, of this distribution, if it were, for instance, two-sided. And so you can construct a confidence interval, and you're definitely, you're now in the game of quantifying the uncertainty of this estimate. Okay, so we are done with the introduction. So let's now move on to the first block of the course, which is the likelihood principle. So the likelihood principle is probably the most important principle in statistics, and so it will occupy us for some time. And let's start with some basic concepts. So I think the best way to introduce them is through an example, and then in the next lecture we'll talk about it in more generality. Okay, so let's consider the following. So let our observations, the capital X's, be IID according to some Poisson family of distributions where this theta is larger than 0. And let's assume that we now have really the data, so the observed, numerical. So assume we have the numerical values x1 to xn, okay, that are the realizations of the random variables. So these are lowercase. Yeah? So once we have this, with the likelihood, with the likelihood principle, We can create estimators, we can create tests, we can create confidence regions, but we're going to start simply with the estimator. And so we can wonder, all right, so is there any way in which we can use this statistical model to find a good estimator? Well, let's note the following. The joint distribution, so the joint distribution of the sample, okay, is going to be this f, and then there is some abusive notation here because generally I was just giving one argument, but let's just have the n arguments. You understand that this is the joint distribution now. So this f is going to be the probability under theta of the capital X1 being X1 up to the capital N, sorry, the capital Xn being Xn, okay? And so this really is the probability, so this is the probability of observing the numerical values, right? Okay, but what is really key is that this is as a function of theta, okay, in the parameter space. And that is totally key because, this gives us the following idea. Well, if this is the probability of observing what we observed, then what about looking for the parameter within the parameter space that maximizes this probability? So what about taking this to be the argmax? Let me not define it like this. Let me just say this is equals. Let's have a candidate here. So argmax over the parameter space of what I'm going to call star, which is this quantity here. Okay, so let's look at that. So for this given example, so this star, by the way, so this is the joint distribution, is going to be, so now by, let me break the page. So this is by independence and the sample being identically distributed is going to be the product, so this is from independence, and then the product of these probabilities. This is from the identical distribution, that they're all equal for the same theta. And you need to remember these kind of things, and that is that this is e to the minus theta, so for the Poisson distribution, I mean, of course. And then, theta, so maybe you need to, and I've forgotten now, to the xi divided by xi factorial. Okay, maybe we can simplify this just slightly by writing e to the minus n theta, and then this here. Okay. No, but this, this looks bad to optimize, right? So what can we do? Well, if we take the logarithm here, then that will become a sum, and actually we'll kill the e here. So it's not a bad idea. In fact, it is the main idea the one uses to construct what we're constructing, which is the maximum likelihood estimator. So likelihood will make sense in the next lecture. And in fact, it can be used, this trick, for many, many samples, because what we're trying to do really is to convert this product into a sum. And that is just true whenever you have independent distributions, that you have some sort of product. Okay, so let's take the logarithm and actually say, so let's note that this theta n that we had above can be rewritten as the argmax over the parameter space now of the logarithm, okay, of this star. And that is, of course, because the logarithm is, is strictly monotonic. So what is the value of this log star for us? Well, looking at that, what we have is minus n theta plus the sum from 1 to n of xi log theta minus log of the xi factorials. Okay, so we need to maximize this as a function of theta, so we take the derivatives. Yeah. The log is going to be minus n plus 1 over theta, and then the sum of the observations, right? And if we wish to guarantee that it is a maximum and not just a minimum or an inflection point, some sort of other critical point, then what we need is to compute the second derivative, and this is given by this. Okay, so if we equate the first derivative to 0, then we get that a candidate is theta n hat equal to 1 over n and the sum of the observations. So that is the sample mean, basically. This is what's called the sample mean. Okay, but we need to check that this is a maximum, so we need to check that the second derivative is negative. Now, strictly negative. So, well, that bit is always negative. This bit is always positive because theta cannot be 0 or infinity because it's not in the parameter space. And this sum, well, this sum is generally positive, but it could be 0 if all of the observations are exactly 0, right? We're talking about Poisson distribution, so that is possible. So then we need to be a bit more careful than just giving the sample mean. And so we need to say that this guy will be the sample mean if it is distinct from 0, so in fact larger than 0 automatically because they are Poisson random variables, and then otherwise we want it to be something arbitrary on this sample space. And why am I writing that? Well, we could have written 0, and that wouldn't be too bad actually, but I am a bit more purist than that, and I like to, I like the estimator to be always living in the parameter space, okay? And it should be, one should be careful with that, and, I think strictly speaking, it should be always in the parameter space, because otherwise, what is the meaning of that estimate, right? But then you'll be wondering, okay, but then this arbitrary value is a really bad approximation actually, right? So we wanted it, ideally to be a good approximation. And worry not, because after all, what we are saying in this case, this case of having all of the observations to be equal to 0 is actually very unlikely for any parameter value. Okay, so you can think about it. And it is more and more unlikely as we get more and more observations, right? So, as you get more and more observations asymptotically, at least one of them is going to be distinct from 0, and then that will rule out this case. And so really this will be well-defined, or it will be close to the true value with high probability. Actually, we don't know if it is close to the true value, so that's something we need to prove. But it would make sense that it's close to the true value. Why is that? Well, remember that a Poisson random variable is, the mean is its parameter, so the theta in this case, and what we're doing here is taking the sample mean. And so therefore, that should be more or less like the theta, which is the mean of the distribution. Okay, so this is, so what we've constructed here is the MLE. So this is the MLE, so the maximum likelihood estimator, that we'll see much more detail in the coming lectures. And later on, we'll go into the Bayesian methodology, again, that we will analyze from a frequentist point of view, and with both of them we'll be able to not only construct estimators but also hypothesis tests, confidence regions, and say something about the asymptotic behavior. And then after this we will introduce a more abstract theory that is called decision theory, with which, through the concept of decision rule, we can unify these inferential procedures that I've been talking about, the 3 of them that I've been talking about, and even more of them, and say, you know, and analyze or talk about more properties of them in a more abstract way. Okay, and then after that, we'll introduce some important, or the most important concepts from multivariate analysis that are very useful for statistics, for statistical analysis. And lastly, we'll go into non-parametric statistics and, you know, more, so basically advanced procedures like non-parametric statistics that I just said, and resampling methods. So I hope you enjoyed this first lecture, and I hope to see you, well, I guess that you download and watch this and the next lecture.